Good morning. Myself, Dr. Paula Shampui, Associate Professor, Department of Chemistry, Institute of Science and Technology. Today, we'll be talking about X-ray photoelectron spectroscopy, its principles, and its applications. Why it is very much important in today modern research. So, X-ray photoelectron spectroscopy, which is called also XPS, it is a surface sensitive qualitative spectroscopic technique. So first of all, this is a combination of X-ray diffraction and spectroscopy. So based on photoelectric effect. So before coming to that photoelectric effect, let me tell that why X-ray photoelectron spectroscopy is very important, because this will utilize X-ray region of the electromagnetic radiation, and this technique can identify the elements that cover the surface. Of course, it will show their chemical state, oxidation state, even overall electronic structures also it is possible. Basically, XPS will be useful for elemental analysis. What kind of elements are present in your sample, that it can be defined by XPS. So this technique is highly useful quantitatively, means how much percentage is present, and that's why it is very much important. That's why I told it's a electron spectroscopy for chemical analysis also. It is known as, we used to tell elemental analysis. It's a powerful technique because it is does not show only the elements present, also it will show that how these elements bond to other atoms. For example, it can differentiate between silicon oxygen bond and silicon carbon bond, and also it will distinguish between different oxidation state of an element. So for example, titanium 3 plus to titanium 4 plus, or iron 2 plus to iron 3 plus, it can easily detected by XPS. So if I talk about brief historic background, so this scientist Henry's Rudolf Hertz, he discovered this photoelectric effect in 1887, but could not explain what is happening in, because that time X-ray beam not discovered, and at the same time that photoelectric effect he could not able to explain it. Then wrong turn. In 1895, he discovered X-rays and he got Nobel Prize in Physics in 1901. Photoelectric effect first explained by Albert Einstein in 1905, and he got Nobel Prize in 1921 in Physics, followed by K.I. Sigban produced the first commercial monochromatic X-ray photoelectron spectroscopy instrument in 1969. Then he got the Nobel Prize in how to utilize commercial application. And in 1913, Henry Moseley also observed different chemical elements. That's also called the Moseley's law. So how it works? If we talk about this principle, X-ray or electromagnetic radiation or photons, it has to pass through a sample, and electrons in the sample surface, it has to absorb the energy from that X-ray, and then electrons from that surface, they will be ejected with certain kinetic energy. So energy of these electrons, it will be absorbed by the detector, and it can be defined their elemental compositions and energies and its oxidation number. So basically electrons of different energies, because different elements are present, they'll follow different paths through the detector, and detector will take all the different electron beams with different energy, and it will able to differentiate the electrons binding energy and produce the spectra. But XPS major problem is that it is not applicable for very low lighter element, for example hydrogen or helium. It is a similar problem as powder X-ray diffraction, because not applicable for lighter elements, and its detection limit are in the parts per thousand range, million also parts per million or milligram per liter also it is possible. So one condition is, first of all, sample has to be solid, because it has to be sample has to be put in a high vacuum. So that vacuum can be 10 - 6 Pascal or ultra high vacuum. So what is photoelectric effect? So you can see this is a metal, lots of electrons will be there, photons fall on it, then electrons on the surface it will absorb and emit. That's a photoelectric effect. Now if we plot electron kinetic energy versus light frequency, so basically photon energy of a photon, it is basically work function of the electron and the energy, kinetic energy. We can tell h nu equal to half mv square, which is your kinetic energy, and the work function phi. So kinetic energy of the electric electrons, it is basically energy of photon minus work function. Now what is work function? It is the minimum energy required to remove an electron from solid to the inner surface to the outer surface. Now this photoelectric effect is basically, it will measure the energy of the electrons, ejected electrons, and it is basically emission of electrons when electromagnetic radiation hit on the metal surface. So these emitted electrons are called photoelectrons. It will have certain energies, characteristic energy, it's called photon energy, and it is directly proportional to the frequency of the electromagnetic radiation or light. So in the photoemission process, when an electron within some materials absorb energy and acquire more energy than its binding energy, then it will be ejected. I'll come back to that binding energy, what is that. So energy of the emitted electrons, that depends upon the energy of the individual photons. So here we can get more clarity. So basically photo emitted electrons, it will have energy maybe less than 1.5 kilovolt. It can escape from the top surface. Now surface sample that skid width can be 70 to 110 angstrom. Now when focus beam with 1.5 kilovolt fall on it, and it will pass, that ejected electron will pass through the detector, and then detector will allow to plot what are the elements present based on their binding energy. Now mostly XPS is surface phenomena. So a surface layer, it is basically 3 atomic layer. It is a 1 nanometer. Distance between the two planes basically 10 - 10. So when you consider the 3 atomic layer, it can be 1 nanometer, and the layer approximately 10 nanometer is considered as ultra thin films, and layer approximately 1 micron, that's called the thin films. And basically physical properties, chemical properties of the surface of the material, it will be different from the inner surface, and in the bulk material this atom will be surrounded all sides. The surface atom generally more active compared to the inner surface in the bulk. That's why surface electron is very much important to know what is the composition, what is the oxidation state. So it will X-ray beam or photo X-ray beam will fall on the sample surface. It will hit the core electron on the surface, and that it ejected electrons will be covered by the detector. So this sample depth generally in nanometer or micron level, and electron signals, it is obtained only depth around 10 to 100 angstrom on the surface, but X-ray can fall up to micron size, but we'll get useful signals which are 10 to 100 angstrom. So X-ray sources, it can produces photons, means that electrons with the higher energy it can be 1253.6 electron volt or 1486.6 electron volt, means that energy it can pass on it, that photons. So normally these samples will be irradiated with photons with single energy, means monochromatic radiation. It will have particular wavelength, monochromatic X-ray radiation. Okay. Now, how these electrons can be ejected? If you see this diagram where this is your K cell, 1s orbital, then L cell, 2s and 2p orbital, then valence band, sorry, and then Fermi level, and then vacuum will be there. Now, electrons will be fall on that X-ray beam. Electrons has to move up to the Fermi level, and that's called the binding energy. Because this binding energy is depending on the atomic number of the element. Because see, atomic number basically it is the charge. More atomic number, it will have more charges will be involved. So stronger means higher electronic configuration, it will have higher binding energy. So when electrons fall, X-ray beam fall on the sample surface, it has to pass the electrons from the inner core. It has to come to that Fermi level, and that's called the binding energy. Now Fermi level to the vacuum means just on the surface of the metals, that element or compound surface, that energy is called work function. And once it touches the surface, then electron will move with the kinetic energy. So that's what, if we consider the conservation of energy, that is H nu equal to binding energy plus work function plus kinetic energy. So what is binding energy? Electrons to kick out from the inner cell to the Fermi level, that is your binding energy. That depends upon its electronic configuration, and then work function is the distance has to be covered from Fermi level to the vacuum level, that is your work function, and kinetic energy is that vacuum level to the outside of the surface, that is your kinetic energy. So if you want to determine binding energy or kinetic energy, you need to subtract it from the energy of photons divided by electromagnetic radiation minus work function minus either binding energy or kinetic energy. So kinetic energy basically ejected electrons or photons, that is measured in XPS. H nu is the incident photon energy that is coming from the electromagnetic radiation. Phi is the spectrometer work function. So it is generally found in a calibration or specific to instrument, and binding energy, which is unknown variable, that is specific to individual atoms. So what are the applications? So it can determine elemental composition, empirical formula, oxidation number, electronic state, binding energy, and of course the layer thickness in the upper portion of the surface. So as I told you, XPS is highly useful for elemental composition. Even it can detect that with which kind of atoms it will have attached, covalently attached. So what is surface? Basically three atomic layer. It is on which the X-ray beam has to fall on it. So ultra thin film generally 3 to 30 atomic layer, and thin films 3 to 600 atomic layer. So thin films is definitely more thicker compared to ultra thin and then the surface. So you can see here ultra thin film, then thin film, and this is your thin film higher up to micron level, ultra film up to 10 nanometer, and surface is 1 nanometer. So if I see its instrumentation, so basically it's your X-ray source, this is your ion source, SIMS analyzer and sample introduction chamber sample has to be put on it. This is another way representation. So X-rays will fall on the sample, and that electrons, photoelectrons, will be moved with different energy, kinetic energy. It will be moved towards the detector. Detector will collect and it will process that signals, and you can get the corresponding binding energy. This is a similar diagram. X-ray beam fall on it. This is the sample range, and then X-ray will ejected beam. It will be collected by the detector. This is a block diagram to get more clarity. So basically, this is your X-ray source. This is your sample, and this is your detector. That photoelectrons will be collected by this detector with different energy. This is the another diagram that X-ray beam fall on the samples, and then there will be vacuum will be there, electron energy will be analyzer will be there, it will be detector will be there, and then finally you can get the corresponding pattern. So this is the video. It has clearly shown that yes, X-ray monochromatic X-ray beam when fall on the sample, then from the sample surface electron will move with different kinetic energy and pass through the detector, and detectors will allow to collect all these different beams with photoelectrons with different energy, and it will process and give the corresponding binding energy curve, and from which we can able to know what kind of element, what is the oxidation state, what is the compositions, we can get it. And this is the typical XPS spectra that shows that signal versus the binding energy curve. So what is binding energy? As I told you, the energy required from the inner shell of the K cell to that Fermi level, that energy is required, that is called binding energy, and that is depend upon electronic configuration, because higher atomic charge or atomic number, binding energy will be more. And you can see the 3d orbitals binding energy is close to 400, whereas 3p around 600 and 3s around 800, because more close to the nucleus, more higher energy will be required. And this is the XPS. So this is your XPS spectrum of palladium metal, and this is a spectrum of silicon metal. And you can see just so silicon, you can see that different compositions you can get it. Oxygen one is, fluorine one is, so different binding energy you can get it. And this is a good example that XPS can easily detect whether it is a silicon or silica is there. So if you can get silicon, if you can get the binding energy 90 to 100, you can confirm this is a silicon. And if you can get higher binding energy 104 to 102, then you can confirm this is silica. So using XPS, one can easily identify whether your composition is having silicon or silica. That's all from my side. So basically that XPS, X-ray photoelectron spectroscopy, it is highly useful in today's um, elemental analysis, where which kind of metal is there, what kind of chemical environment is there, or what kind of oxidation state is there for that particular element. We can easily get information using XPS. So interesting thing is that X-ray diffraction is used uh, to get that elemental analysis, and as that it is particular spectra arrangement, so that's why this is a combination of diffraction and spectroscopy, and that's what X-ray photoelectron spectroscopy. This is the one such case where both X-ray beam and electron spectroscopy are combined to get the valuable information about the surface of a metal. Okay, so thank you. Here I stop here.